Okay, good afternoon everyone. Good afternoon. So as I mentioned last class, I'm going to start a problem, take it from scratch and then draw the Bode magnitude plot. Okay? So here is a problem. So we have a series combination of elements along with some in parallel as well. Alright, so I have a source which is an ideal voltage source, okay, so, and this is a sinusoidal input voltage, so V of S, Vs of t is a sine omega t, which means that this is a problem where you can apply the frequency response approach, okay, and I have a capacitor C, inductor L, two resistances R and R. Just for simplicity, I've assumed them to be the same, but they can have different values, varying values. And what are we supposed to do? V0 is the output, so this is the input. And V0 of t is the output. Okay. What are the things we need to do? Is obtain the system model. And then draw Bode magnitude plot. When I say system model, this essentially implies a differential equation that relates V0 and Vs. Okay, so this is an ODE. Relating V0 and Vs. Bode magnitude plot, we know this, magnitude m versus omega. And for all these problems, I have a specific method that I follow. Okay? It works for the most part. The problem can be complicated, but you just have to do it step by step. It takes a lot of patience. So here is the first step in a solution of this type of a problem. The first step is, I always use the impedance method. You are welcome to use whatever method you've learned in electrical systems, circuits, that's completely fine with me. What I present is using the impedance method. It is the easiest of the methods, okay, because I get the system transfer function directly without doing too much. So I take the system, draw it in the Laplace domain. So that's the first step. When I draw it in the Laplace domain, I replace each of these elements by their impedances. Okay, so the impedance of the capacitance element is 1 by Cs. People in the back, can you see my writing? 1 by Cs. Okay, then I have the impedance of the inductor, which is Ls, and then R and R. Capital R, capital R. My output voltage is now V0 of S in the Laplace domain. Capital V. Okay. And input voltage is obviously Vs of S. The small squiggle inside this symbol of the voltage source implies that this is a sinusoidal voltage source. Okay. All right. Now, I select any one of the nodes to act as the ground node. So I'll just choose this node here to act as the ground. And let's give all these nodes some names. So start with A, B, C, and D, and so on. So node A, node B. I'm going to call this node D because C is used for capacitance. Then here is node E, and then F, and then G. And I also write the voltage values at these nodal points in the Laplace domain. So this is VA of S. This is VB of S. V suffix D. Obviously, if I have a ground node, then the voltage there is 0. Right? So this is VE of S is 0. There are no elements between E, F, and G, which means all of them are also 0. Okay? The potentials there are also. So this is VF. Does this make sense to everybody? Standard practice. And for me, typically, the main branch of the circuit is the branch which arises from the source. Okay, that's where the energy of the circuit is obtained. Right? And so I call the branch current through that main branch, and you can passive sign convention. Let's assume that the flow of current is clockwise. Okay, and so I start off with labeling the main branch current as I of S. And once it reaches the node B, it branches off into two, as you know from Kirchhoff's current law. So I'm going to have an I1 of S, which is also the current through the second resistor there. And then I have an I2 of S. And once again, can everybody see my figure properly? People in the back, on the sides, and so on. Okay? Let me know if you cannot see my writing. Okay? All right. So far, this is nothing new. You've seen this in circuit classes. Then I write down the voltage differences. Okay, so first of all, Vs of S is Va minus Vg. Obviously, Vg is 0, so this is just Va. And then V suffix naught of S, which is the output voltage across the resistor, is V suffix D minus Ve, which is just V suffix D of S. Okay? Kirchhoff's current law at node B, I of S is I1 plus I2. This is KC. Okay, once again, this is old news. The key step in all these problems is the following. You want to somehow, hook or crook, you want to relate the main branch current to the output voltage. Okay, so that's the first thing that we seek. Okay, so relate I of S to V naught of S. Okay, so this implies that I have to relate I1 of S and I2 of S, and I could add them. Okay. Second step is I use the method of impedances. You obviously are looking at this as much as I do. You see these two are in series, same current through them. Then those series arrangement will be in parallel with this guy. And then eventually I'll have a total series arrangement. Right? So that's a method of impedance. I use that to reduce everything. So that I can relate the main branch current to the source voltage. So relate Vs of S by I of S is equal to some effective impedance. Okay? So we need to find this effective impedance. We need to find the first relationship. And obviously you know that I have a relationship between I of S and V naught. I have a relationship between I of s and Vs. I combine the two, I get my system model in the frequency domain, okay, or in the Laplace domain. Combine, you get the transfer function of the system, which is the output Laplace transform by the input Laplace transform. Once I have the transfer function, I know everything about this system. Right, so this is the general procedure. And let's work on this piece by piece. I'm going to refer back to my figure on the top panel there, so I'm not going to redraw everything. The first thing I notice is, look at the last resistor R. I can relate the current I1 to V0 by saying that V0 by I1 is equal to the resistance R. Okay? So between nodes D and E, is equal to R, capital R, which means that I1 is V0 divided by R. And you are under no obligation to follow this procedure. If you have learned something different in circuits, I just need the same answer. I don't care. And that's my first equation. Then I also notice that, okay, I2 of S, if I look at the nodes B and F, okay, so I can say that the voltage difference VB minus VF divided by the current is equal to the impedance across that branch, and that's going to be LS, right, which means that I can get rid of VF because that's connected to the ground node and no elements exist between the two. So I2 of S is VB of S by LS. Okay, so two equations. My next step is to take VB and try to relate that to V0. Okay, so if I do that, then I have I of S in terms of V0, right? Because I can just add these two up. Okay, so somehow relate VB to V0. How do you do this? And here you have to use some inspection. Okay, this is not straightforward. But if you have solved a problem like this, it will become straightforward. Look at the nodes B, D, and E. Okay, look at nodes B, D, and E. Why am I looking at those nodes? Is because I have the voltage VB at the node B, and then the output voltage V0 is between the nodes D and E. That's why I'm looking at those three nodes. Okay? If I look at those three nodes, then obviously I know that the same current is flowing through the resistors, so they are in series, and so the total potential drop divided by the current is equal to the total impedance. Okay? So I have VB minus V suffix D plus V suffix D minus VE. This is the total potential drop across the two resistors, across the nodes B, D, and E, difference between the nodal voltages, divided by the current. This is equal to 2 times R, because those two are in series. Does this make sense to everybody? This is the critical step here. Why am I focusing on those three nodes? Is because voltage VB is defined at the node B, and between D and E I have the output voltage V0. Okay? And obviously VE is 0. I have plus VD, I have minus V suffix D, so those two cancel off. And so I have VB is equal to I1 times 2R. But you obviously see what I'm saying, right? Because I1 is related to V0. So now I have the relationship between VB and V0. So this is nothing but 2R. Instead of I1, it's V0 divided by R. So that is just 2 times V0 of S. And if I know V suffix B, I go back to I2, substitute. I2, which was VB by LS, VB is now 2 times V0. So that's just a 2 by LS. Right, the problem that I see with circuits, these people immediately start jumping in, start using Kirchhoff's current law, Kirchhoff's voltage law, use all the laws in your mind, and then you go mindless because we don't know what to do. Right? So here you have a procedure which mostly works, okay, unless your circuit is really complicated. In that case, good luck to you. So if I now take I2 and I1 and combine them, I have I of S, which is a sum of these two. Right? So I have this creature here, that creature there, sum them up, and so I have the first thing, and that's knocked out of the game. So I of S is I1, I2, so this is just 2 by LS, and then I'm going to have 1 by R, V0 of S, or simplify it, take the common denominators and so on. So that I of S is LS plus 2R by R LS V0. I want to pause for a minute, or less than a minute, and see if there are any questions. First piece of the puzzle, finished. Second piece is easier because here is where we start making use of our idea of impedance. Impedance in series, they have the same current flowing through them. You just add them up to get the effective impedance. Impedances in parallel, they have the same voltage difference across them. You use a reciprocal rule. So I start off by simplifying my circuit first and seeing that the R and R are in series. Add them up and then do the combination of the parallel LS and then a series eventually. Okay? I'm going to bring the top panel down. We're going to revisit this particular relationship once again. Okay? Maybe I should write it out somewhere here. Right, so now reduce using impedances. Take the two R's, they are in series, add them up. Okay, so the first reduction is 1 by CS LS I'm going to call it Z1, and Z1 is R plus R, which is 2. This is Vs of S. Then the second reduction, Z1 and LS are in parallel. So replace them by a single one. So 1 by CS. Call it as Z2. Okay. This is I of S. Vs of S. How do I calculate Z2? Reciprocal rule. So 1 by Z2 is 1 by Ls and 1 by Z1, which is 1 by 2 times R. Simplify and flip everything. Z2 is going to give me 2 RLS LS plus 2. No matter how many branches you have, this is like working on a problem in trusses. You start off with one and then you slowly work your way back to the member or the truss bar that you need. Okay, so same idea here as well. And obviously you see these are all in series, so I replace them by my third step, the third reduction. This is now Z effective, right, which is what we are looking for. I of S Vs of S, and what is Z effective? Is the sum of Z2 and 1 by Cs. Which is 1 by Cs, then 2 RLS by all this stuff. Take common denominators. Z effective. After we take the common denominators, it becomes the following. So this is going to be 2 RLS multiplied by CS, so I'm going to get a second order system. I don't need to get a third order system. If you're getting a third order system in our particular course, alarm bells should start ringing. Question?
Why do you reduce your circuit to step 3 if you're like, originally if you're doing like finding a transfer function, it would be over the voltage drop across Z2, right?
Yes, no, across Z2, across Z1.
Yeah.
Yeah,
Right?
Absolutely.
Why would you reduce it even more? That would get you like entire voltage drop. How would you get?
Right. So the idea is, you see Z effective, if I write it out here, this is essentially Vs by I of S. Okay? So if you see this here, I can now find I of S in terms of Vs. Just a few minutes ago, we have I of S in terms of V naught, which means if I equate the two, I get my system transfer function. Makes sense, right? This is my method, my technique. You're not obliged to follow this, but this works 100% of the time that I've taught here, which is quite a long time. Okay, so Z effective, it's not my method actually. Z effective is take common denominators 2 RLS multiplied by CS 2 RLCS square. Great. Then I have the LS plus 2R multiplied by 1, so that's plus LS plus 2R. One of the primary things you should practice, if you have not already done so, is to write systems in the proper form. Right? The highest order term, second highest order, and so on and so forth. Okay? That's really important. And the denominators. This is equal to that guy. I'm going to pull this panel up and write I of S eventually in terms of Vs. cross multiply, so that I of s is now Ls plus 2R multiplied by Cs multiplied by Vs divided by 2RLCS square and so on. Equation 1, right? That's equation 2. So obviously IS and IS are the same in both the equations. So now you see the utility of what we've done. I have the relationship between the two, Vs and V0. So I just grab that result, which is Ls plus 2R V0 of S by R Ls. I just use that result there. Does this make sense to everybody? I can pause for questions. Basic idea is I need to relate V0 and Vs, right? How do I do this? Using Kirchhoff's current law, first you split the current into branch currents, and then you relate individual branch currents to the output voltage. Use the method of impedances, reduce everything to one big lump mass, which is the effective. That will give you a relationship between I of S and Vs. And obviously the two equations are the same, so I can now say that I have the relationship here. Now watch this. Ls plus 2R, Ls plus 2R, let me rewrite this just for my own convenience. 2RLCS square. This is equal to I can cancel off the common factor of Ls plus 2R, so one less headache. Cross multiply, so that V0 of S 2RLCS square. Take the RLS, multiply with the CS, and that becomes an RLCS square Vs of S. All I did was cross multiply. Invert it. If I see an S square and if I attach it with V0, that becomes a V0 double dot. If I see an S, I attach it with V0, it becomes a V0 dot, right? As I invert it back into the tangent. So if I write the inverted result, and just for Laplace inverse, S square is etc. So that my system equation, my system model, which is really nicely obtained here, is 2 RLC V0 double dot L V0 dot 2R V0. Watch out. RLCS square Vs, if you invert it back, is Vs double dot. This is a system with numerator dynamics, as is the case for many of the problems that you're going to solve or already are solving in your homework. That doesn't mean that we cannot use the techniques we've already learned. Okay? And this should also tell you, if you write the transfer function, which I'm going to write, this is the system model. Okay, so in the problem asks you for a system model, this is the system model. The transfer function is just RLC S square by 2 RLC S square. This is the system transfer. Numerator dynamics. S square. What does it mean? I have a repeated 0, right, because of the presence of S square, but that is at the origin of the system, because the root of that is 0. So this is a repeated 0 at the origin. It's a funny thing. And then obviously I have a second order system, so I'm going to have a pair of poles. They could be complex conjugate, they could be real repeated, real distinct. Who cares? We know how to handle all of that. With your permission, I'm going to delete or erase this portion of the book. Okay? Questions, please. Yes, yes.
Just as a check, will there always be a term that cancels? Because I noticed like on the homework problem, there's also two, like for both of them, there was a term that canceled.
Usually, but don't take my word for it, because if you have circuits where there are some additional branches on top of one branch or the other, right, then it may not so happen that way. But the procedure always works. Any other questions, please, before I move on? Yes?
You want to convert that into standard form?
I'm going to do it. I'm going to. To do it, I'm going to give some numbers so that we have a nice problem. And the niceness stops in the lectures. Okay, let's give it some numbers. Okay, so let's say that R is 2 ohms, L is 1 Henry, C is 1/4 farad. It's a pretty large number, C, but it's okay for the sake of our problem. I first write my system model. Okay, so if I look at the system model, substitute 2 times RLC. So 2 times 2 is 4, multiplied by a factor of 1/4. So the first term in my system model becomes just V naught double dot. Okay, this is after just crunching the numbers. Then the second term is L V naught dot, so that is just going to be 1 times V naught. 2 times R times V naught, so that's going to be 4. And RLC is 2 times 1 times 1/4, which is 1/2. So this is 1/2. VS double dot. Yes, question.
Where did the 2 come from next to R and naught?
Where did the 2 come from next to R and
R V naught of T. We go from R times V naught of S.
Oh yeah, I see.
Oh.
Swallowing a factor of 2. It was supposed to be there. We
Yeah.
see that.
Okay.
Thank you. I usually swallow a factor of 2, as you know, from calculating T peak values as well. Or maybe that's the extra factor of 2 I was missing before, which is put back here. Okay, that was pretty bad. All right. So I go back to my problem. I look at the standard form of the system. What's the standard form of the system? Is x double dot 2 zeta omega n x dot omega n squared x is some g of t. This is a second order system, so obviously on inspection omega n squared is 4, which means omega n is 2, and then 2 zeta omega n is 1, which means zeta is 1/4, which is less than 1/√2, which is less than 1 obviously. I should say less than 1, that's the move. It's an underdamped system. Okay? Not only is it underdamped, the zeta value is 1/4, which is 0.25, which is less than 1/√2, which is 0.707. So I have a physical peak in my problem. Okay, I'm going to write that statement next. Okay, so zeta, which is 1/4, is between, which means that the peak exists, the peak happens to be at the resonant frequency value. So omega r is omega n times this factor of 2 remains. Okay, this is the same as what we've done in lectures. You substitute, it gives you 1.86 approximately. Radians per second. The peak value is 1/2 zeta 1 minus zeta squared. Okay, so this is where I made the typo. There was a factor of 2 in my notes. Please get rid of it. It will change everything. Not by so much, because you're going to disregard that term anyways. Okay, so what we're going to say next is, when damping is very small, this factor of zeta square is very small, so that we can approximate this to be 1/2 zeta. This is for small zeta. And what is small? That depends on who you are. But if you're a mechanical engineer, small is between 0 and 0.5, typically. Okay? So we will employ this approximation. It's a small zeta. We like zeta to be present in all our problems, okay? Because that reduces the magnitude of the peak. Alright, so this is what we have so far, and we need to draw the Bode plot for this problem. And I want to stop and see if there are any quick questions. To draw the Bode plot, obviously we need to look at the transfer function. We need to write it in the proper form for the Bode plots. And then we will draw the magnitude too. Okay? Yes, question.
After you change your formula, because you add the 2, would the system still go to infinity?
Oh yeah, obviously.
If it was
that doesn't make any difference.
if zeta was at 1 by square root 2 though?
Yeah, obviously. Yeah. The system response will be going to 0, not at 1 by square root of 2. That depends on whether you have damping or not. I mean, at 1 by root of 2 is the largest value that you get, typically. Right? And if you go beyond that, then you get omega r to be 0. So if your omega r is 0, then this does not necessarily have any meaning to it. So it's not as if this goes to infinity. This goes to infinity when zeta is 0. But when zeta is 1 by root 2, you no longer have a resonant frequency. So the physical limit is boxed in. All right. So let's draw the Bode plot. So go back to our transfer function. T of S R L C S square 2 R L C S square L S 2 R. Substitute for the values of R, L and C, you get the following. 1/2 S square S square S. Okay. This is not in the standard form. It's an underdamped system, so you've got to rewrite it in the standard form by dividing through by omega n square. Right? So standard form is 1/2. Factor of 4 is omega n square, so bring that out. S squared by 4, S by 4, and 1. Take the factor of 4, attach it to the factor of half, it makes it 1/8, okay? And so, one by 8 a square. I'm going to leave this as an exercise, but if you obtain omega n, which is 2, and if you obtain zeta, you'll figure out that this is essentially the same as the following. S squared by omega n square, 2 zeta s by omega n plus 1. Okay? So here omega n is 2, zeta is 1. All the values check out, so we are good to go. This presence of s square means that I have a repeated 0. At the origin. The significance of these things will be more clear once you do control system design, when you're going to draw the root locus plots and so on. And so that will tell you how to control the system behavior as a function of time. Okay, so we are not going to go into those things today, or neither in the next few lectures. Frequency response function. P of j omega, so that's 1/8. Can't do much about that. J omega whole square, so that's going to give me minus omega square. The denominator is the standard one that we have been writing in the past. 1 minus omega square, omega n square, 2 zeta, omega by omega n. Don't worry about that minus omega square in the numerator, it's not going to affect anything. Because when I take the magnitude, it's going to be the square root of the sum of the squares of these things. Right? So, magnitude of the FRF is 1/8, still remains. Square root of the sum of the squares of the real and the imaginary part, so the negative sign vanishes, so I just get omega square. And here I have 1 minus omega square, omega n square whole square, 2 zeta, okay. You do it this way if you have an underdamped system. If you have an overdamped system, we looked at it in the last lecture, you write it in a slightly different form, right? You take out the zeros, frequencies, you take out the 0 poles, the roots, and so on, and then write it out. So here, I'm now going to go into the Bode plot regime. So M is 20 log 10 T of j omega. With your permission, can I take some shortcuts? Okay, so I'm just going to rewrite it. So if I say this is just split into 3 parts, it's 20 log 10 of 1 by 8, right, the first piece. Then 20 log 10 of omega square, which becomes 40 log 10 of omega. And then the last one is I have a square root. I take the log 10, it becomes a minus half because it's in the denominator. So this is minus 10 log 10 plus all of the rest of it. zeta omega by omega n whole square. Log 10, 1 by 8, 20 times that, it becomes minus 18.06. Okay, so many decibels. 20 log 10 of omega square becomes 40 log 10 of omega. So if I have a repeated 0 at the origin, I'm going to get an increasing slope of 40 decibels per decade. Okay, so that becomes plus 40 log 10 of omega. The last term remains as it is, can't do much about it. So that's minus 10 log 10 plus and as usual I call this as M1, M2, M3. Okay? M1 is simple, it's a straight line. M2, yes, question, quick question.
M1, M2, and M3 all include sines too.
Absolutely, absolutely. That's what I've been talking about last lecture as well, and I'll be writing it out again. Okay? All right, question.
Does the first value in like the log 10, the 1 minus omega squared over n squared is supposed to have?
Oh, yes, yes, there's a square. I'm missing. Thank you, thank you, thank you. Okay, so M1 is a straight line. Minus 18.06 decibels is a straight line, not much thinking involved there. Second thing is M2 is plus 40 log 10 of omega. This is nothing but a straight line, obviously on the log plot. It increases by 40 decibels for every decade of omega. Increase of 40 decibels per M3 minus 10 log 10 all of that stuff. We looked at this last lecture. Recitation, please go to recitation if you haven't done so. Please look at the recitation notes. You split this into a low frequency asymptote and a high frequency asymptote. Right? The low frequency asymptote becomes 0. Please look at last lecture. Omega much less than omega n. M3 low is 0 decibels. For omega much greater than omega n, M3 high is minus 40 log 10 of omega by omega n. The high frequency asymptote tells you that as soon as I cross omega n, which is where both these two asymptotes meet each other, I'm going to see a drop of 40 decibels for every decade increase in omega over omega n. Okay, so M3 high, 40 decibels per decade drop. For the ratio of omega by omega n. Okay, so if omega is 2, that's equal to omega n. If omega is 20, that's 10 times omega n. That's 1 decade. If omega is 200, that's 100 times omega n, so that's 2 decades. And for each decade, I see a drop of 40. Does this make sense to everybody? I'm going to pull this panel down, assuming there are no questions so far. And we are left with the last step of plotting this. And I usually take the safe route. I write down M1, M2, M3, tabulate the values, plot it in a tree. Okay? All right.